Hello, I'm Peter Knight and this is number 2 in our series of short lectures on geomorphology. I'll talk quickly, so use the pause button to slow me down. Geomorphology is all about the way that geomorphic processes, which are controlled by environmental factors, act on Earth's surface materials to produce landforms. Linked assemblages of landforms are landscapes, and if we consider landscapes along with the processes that form them and the materials that they're made of, we're talking about land systems. These concepts are the building blocks of geomorphology. My key point for this lecture is that the processes that create landforms depend partly on the energy available to drive the processes and partly on the load or resistance to be overcome. Individual landforms can be explained in terms of this relationship between energy and load. Processes that we're interested in include all of these. You'll have no trouble finding them in any standard geomorphology text. If we lump all of those geomorphic processes together, we could argue that landforms are created either by material being transformed in some way, for example by weathering, or by material being picked up and moved around by erosion, entrainment, transport and deposition processes. Not many landforms are created by weathering alone. Most landforms require the movement of material. For example, the classic weathering landform, tors, are generally thought to require either deep tropical weathering or subaerial frost weathering in combination with the removal of the weathered detritus. Most landforms can be interpreted either as packets of sediment in transport, like the sediment in this proglacial outwash in Iceland, or sediment that's been deposited, like the moraine in front of this little glacier in the Rockies, or voids where material has been removed, like in the Yellowstone River Valley here. But many landforms are complex combinations of all of these. The hills in the top right picture here, for example, are erosional remnants left behind after removal of the material between them, so the landscape is defined really by the voids between the hills more than by the hills themselves. But the valleys are cut into older deposits that were laid down in a previous stage of formation of the landscape, made of material that was previously eroded elsewhere and brought to this location. In the lower picture, whether we think of the dunes as deposited material or as material in transport depends on the time scale, and if they're in transport, then at the local scale there must be both erosion and deposition going on within the dune system. Two important factors are involved: the energy available to drive the process and the properties of the materials that are being affected. The ability of the river here to erode and undercut the outer bank depends on the power of the stream and the strength of the bank materials. The Hulstrom curve, which illustrates the power required to entrain or transport particles of different sizes in a stream, is a classic example of this kind of analysis. Except for the very fine-grained materials that cling together and are hard to entrain, the amount of energy, or water velocity, required to entrain a particle increases with the size of the particle. It takes more energy to move a big boulder than a small pebble. Fast-flowing water can transport bigger particles than slow-flowing water. To predict what will be happening in our stream, we need to know about both the velocity of the water, the power, and the size of the particles, the load. We can apply similar thinking in most geomorphic situations. For example, coastal erosion is controlled by wave energy, determined by things like wind direction and fetch, and by the strength of the coastal materials. More resistant rock is less susceptible to erosion and likely to create stable cliffs. Weaker materials are more likely to be eroded and won't support steep cliffs. A classic example that illustrates the importance of rock strength in coastal geomorphology is Lulworth Cove, where a coastal strip of resistant rock has been breached in this particular location, allowing erosion to affect the softer rock behind it. The important idea that geomorphic processes are strongly controlled by the geographical distribution of energy can be illustrated by looking at alluvial fans. Where the stream emerges from the mountains as a single channel, it has a great deal of energy and can carry both small and large particle sizes. As the channels split and spread across the fan, each small distributary has a progressively less and less energy as we move downstream. Consequently, the competence of the streams to carry larger particle sizes gradually decreases downstream, so there's a clear pattern of deposition, of coarser material near the head and finer material towards the toe of the fan. Local conditions complicate the picture, but that general rule applies because the geography of stream energy controls the geography of sediment transport and deposition. So I've made quite a simple point in this lecture, that geomorphology can be approached by considering the interactions of energy and materials. In the next lecture we'll firm that up a bit by talking about the concepts of shear stress, strength, strain, geomorphic thresholds and sensitivity. That'll give us some basic tools for trying to understand how landscapes work.